Okay, I think we can start. So, good morning to everyone. Warm welcome to the community of the Geoplanet Doctoral School, the directors of the institutes forming our school, employees and doctoral students. My name is Radek Smolec. I'm the head of the Geoplanet Doctoral School. Our school was formed nearly 3 years ago by 7 institutes of the Polish Academy of Sciences, Space Research Center, Center for Theoretical Physics, Institute of Geophysics, Institute of Geography and Spatial Organization, Institute of Geological Sciences, and Institute of Oceanology, and of course Nicolaus Copernicus Astronomical Center as a leader of the school. I will now ask the center's director to give an introductory word, please.
Thank you. Good morning, everybody. If there is someone in the different time zone, good afternoon. I mean, if there happens to be someone far away to the east. Well, as Professor Smolec just mentioned, the doctoral school is a relatively new idea in Polish educational system, established just a few years ago. The idea is that the doctoral level of education should be more interdisciplinary. We should combine a number of disciplines so that the PhD students have a chance to do research, to collaborate within not just their own discipline represented by a particular institute, but in a more interdisciplinary environment, which should be stimulating for your research, for your thinking, for your way of forming as a scientist, that you will see more than just a single discipline. And indeed, the Geoplanet Doctoral School represents a number of disciplines: physics, astronomy, earth and environmental sciences, and also some of the engineering disciplines. Again, as Professor Smolec mentioned, the school is run or is created out of 7 institutes of Polish Academy of Sciences. Polish Academy of Sciences is a just purely research institution in Poland, as opposed to universities, which do education at the higher level and also research. Well, we are good institutes, graded very good or excellent in the ministerial rankings. So in this sense, you are in good places. Our scientists do world-class research. They are experienced supervisors, researchers and supervisors. In many cases, they were able to win grants to fund you, the PhD students, in very competitive national and international competitions, which speaks for the quality of your supervisors. Well, in principle, this is called PhD studies or doctoral school, with the emphasis on education. But I will always say that this stage of your life is really the first stage of doing research, beginning of your scientific research career. And in my view, you should view it as such. So it's not just learning new things. I mean, you do have to learn a lot, but while acting, while doing research. And I think the main goal should be for you to learn how to be a scientist, what it means to be a scientist, what is the craft of doing science. And again, coming back to my previous thought, you are in good hands. I mean, not only the institutes, but also your supervisors. So use these 4 years use it to the fullest, use it well, so that after the 4 years, after obtaining your PhD degree, which should be a natural conclusion of these coming 4 years, you are, well, you know how to do science, you are well prepared for doing the research on your own. In the next stage, the postdoctoral stage, you will work usually with the help of someone, but you will be slowly or perhaps fast maturing as a scientist, so that your final goal would be to be a independent, mature scientist, to be able to lead your own group and conduct world-class research. So once again, welcome in reality or virtually to Poland, Warsaw, Toruń, Sopot, any other place that you may end up doing your research. Let the climate be kind to you. Find a good place and do spend the 4 years fruitfully, so that this is really a good time and a productive first stage of your scientific career. Thank you. Going back to you, Radek.
Thank you very much. The students that we first admitted to our doctoral school are now at the halfway point of their education. Midterm evaluations in the institutes of our school have been either completed or are in progress. I hope that these first years of education have brought much satisfaction and interesting scientific results. More students are beginning their first year of study. This year, we have admitted a total of 18 students, and thus our school already has 62 students, more than half of whom come from abroad. We try to constantly expand our educational offer. This year, students will have the opportunity to attend several interdisciplinary lectures common to all institutes of our school, including advanced statistical methods, a lecture on climate change from the ocean perspective, and a lecture on selected topics in cosmology. We are planning a summer school for our students in the spring. It was supposed to be held a year ago, but we decided to postpone the school until this year, with the hope that it can be held in the real world. The theme of the school will be climate change, which is perfectly in line with the Nobel Prize in Physics awarded this year. As a teaser, in November, we are hosting a short series of 3 lectures related to Nobel Prize winning research. I hope that the coming year will bring us a lot of satisfaction, interesting scientific results, and opportunities to meet, not only in the virtual space. Now I would like to invite you to inaugural lecture. Dr. Jakub Chonjala from the Institute of Geological Sciences will take us beyond Earth to explore Mars. Jakub Chonjala is a doctor of natural sciences, graduated from the Leibniz University in Hanover, Germany. He is a geochemist, a mineralogist, and planetary geologist, currently working in the Institute of Geological Sciences. He investigates the migration of metals and searches for ore deposits in yet unexplored areas. He was the science member of the International Ocean Discovery Program expedition that started drilling to Earth's mantle. He is also involved in projects of the International Continental Scientific Drilling Program and European Space Agency missions to Mars. He's also a principal investigator of several research grants, and he leads the MIRORES team designing a far-infrared spectrometer for the detection of ore mineralization on Mars and on the Moon. Please, the floor is yours.
Thank you very much for this kind introduction. Maybe I will share my screen at first, not to forget. Okay. Thank you again for the nice introduction and for having invited me to give this inaugural lecture to our Geoplanet School doctoral students. I feel really honored to take this task this year, and especially because, as you mentioned, as the director of the doctoral school mentioned, this Geoplanet School is an interdisciplinary school. It is about earth sciences, but it is composed of many institutes, including geophysics, oceanography, geography, astronomy, and geology, of course. And therefore, this lecture, although it is mostly about planetary sciences because it is about Mars, but it can be viewed from different angles. So to study Mars, we need to use various methods, of course, based on geology, astronomy methods, geophysics methods, and even geographic and oceanographic methods, as I will show in the lecture later. And this picture is provocative because we talk a lot about space mining in last years, and in many concepts, space mining works like we go to a planetary body of a small size, and we take this to Earth to use this on Earth. On Mars, it works differently because we cannot take metals from Mars, or any kind of resources. It's just too expensive, but we need them to use them in situ. And this is because the exploration of Mars is proceeding very fast. And we want to be there, we want to explore. And you can see on this image, I showed this in many talks in last years, and I have more and more problems actually. These letters become smaller and smaller, the images become smaller and smaller because there are more and more missions. Maybe I will minimize this. Okay. And so, but still you can see a pattern here. We can distinguish, I think, 3 stages of Martian exploration. So the first one was related to Cold War, and you can see in the flags that there are Soviet Union flag here, United States. These were these 2 empires which fought who would go to Mars first. And this period went from 60 to 75, more or less. And US especially was quite successful with the first orbiter on the orbit of Mars called Mariner, and with the first lander on the orbit of Mars called Viking. Then we had a hiatus, maybe hiatus is a geological term, stagnation is a better term. So we had a stagnation between 75 and 95. There were almost no successful missions, just a couple of not very successful, actually almost lost missions, like here. And then from 95, we had a development again. And you can see this on this image, 96, 0 active mission on Mars, 2021, 11 active missions already. So there were more and more missions, more and more players involved, and this race became global. So we have JAXA, Japanese agency, we have our European Space Agency, we have Indian Space Agency, and finally, in the last year, also United Arab Emirates, and also China started its space and especially its Mars exploration. So in the last year, there were 3 new missions, 4 were planned. ESA rover, unfortunately, it was delayed again, mostly because of COVID reasons. Also, some problems with parachute systems, but still, even without ESA rover, which is on a good way to be launched in the next year and to land on Mars in 2023, but even without that, we had 3 new successful missions to Mars. So this is kind of a record, best performance ever. And among these 3 missions, we had 2 rover missions. One, which everybody knows, this is Perseverance mission with big American rover, but there is also a small rover. This is a lander, but there is also a rover involved in the Chinese mission, which landed more or less in the same time, and it's operating on the surface of Mars also successfully. Apart of that, there was also this smaller mission, orbital mission of United Arab Emirates, and it's also successfully placed on the orbit. And of course, one of the most hot topics in the Mars exploration this year was this first flight, this is actually already third flight, of the NASA helicopter, NASA drone Ingenuity, which is controlled by the Perseverance rover. And this is a big event because Martian atmosphere is more than 100 rarer than the Earth atmosphere, which means we need 100 higher lifting force to fly in the Martian atmosphere. Therefore, it's so difficult to achieve. And the propellers must move very fast. This must be, of course, also quite light. And as you can see, it came back, it's successful. So why we have so much interest in Mars? There are 2 reasons, actually. The first is well visible on this image. Mars is one of the 2 our nearest neighbors, except for Venus, of course. But in contrast to Venus, it has relatively mild temperatures, we can say. With Venus, we have more than 400 Celsius degrees, sometimes, or actually always. On Mars, temperatures during the day can be above 0, even 20 or 30 Celsius degrees. At night, of course, it's tough. It can be minus 100 Celsius degrees, but it's imaginable for people. You saw people protesting in Yakutsk this year during protests in Russia, and people were walking in temperatures like minus 60 degrees. So temperature won't be the largest problem in Mars exploration. Of course, there is also Moon on the way, and there is also a lot of interest in Moon too, but we've already been on the Moon. So people want to explore more, and this is our curiosity, which pushes us to other targets. So the final target of all space agencies nearly is Mars. So this is a common view of many agencies like NASA, JAXA, ESA, and agencies which make ESA, including DLR and CNES, and also our Polish space agency. But there's also private sector which wants to explore Mars, and it's also Moon here is kind of intermediate target, very important also, but the final target is always Mars. And I've showed here on this slide that public agencies are quite cautious. They talk about about sending humans to Mars not earlier than in 2040. Private sector is more optimistic, probably too optimistic. 2029 seems like very fast in 8 years, but maybe private sector will be first on Mars. Maybe they will manage to do this in 2030s already. So as we want to explore Mars, we want to colonize Mars, we need resources. We need how to use resources there and how to find resources there. And therefore, a lot of space agencies in the last 3 years started to prepare special strategies to search for resources. So this slide is focused on Europe, of course, and Luxembourg Space Agency is a leader here with first space resource strategy or space resource report made in 2018. Then ESA followed up, European Space Agency, and then both agencies combined their forces and created ASRIC, which is European Space Resources Innovation Center, and it has aims to facilitate all prospecting on Mars for science and business, and to make plans for future mining and even constructions and production using space resources on Mars or on Moon. And when we talk about resources, water is, of course, the most important. It's something sine qua non. It's impossible to live on Mars or Moon without water. And therefore, we will start with this. And water may seem to be problematic on Mars because it's a quite dry planet at the moment. But in the past, there was a huge ocean on Mars, especially in the northern part. And now, of course, it's evaporated mostly, but plenty of water is still caught in ice. And we have 2 polar ice caps on Mars. This is a cap from the north, but there is also another cap on the south. And it's quite large. It reaches 75 degree north, this cap here. But of course, it seasonally changes more than our Earth ice cap. So this is one feature. Another difference is maybe that except for water, this is also composed of a thin layer of CO2. But we don't need to go so much north to find water on Mars or so much south. There is water also on lower latitudes, sometimes even as low as mid-latitudes, like 30 degrees north or south. This is an example from relatively north, and you can see here at the bottom of the crater, at the slopes, at the northern slopes, you can see the orientation here. So these are north-facing slopes, and you can find frost or ice in these shaded craters. Finally, we have also water underground, and it extends quite far towards the equator. Of course, at north, it's quite shallow. Towards south, or better to say towards equator, it becomes deeper and deeper. But generally, water seems not to be an issue on Mars. It seems to be quite common, ubiquitous. And scientists got interested with water very much, not only because we want to use it in the future, but it also can show us where we can search for ancient life. If there have been any life on Mars, it could have been in such places like this, like an ancient lake, which is found in the Jezero crater, and therefore the last rover of NASA, Perseverance, has been sent to this location. Now I will show you a movie showing the landing of Perseverance, and I will comment only a little bit because it has an original comment in English.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Applicant indicates chute deployed.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
So you saw in the first part, parachute was deployed and then heat shield was separated from the rover, and now rover is on the way to the Mars. Now you can see the Mars surface, for example, impact
Nav
rate.
filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars.
And now we are
Perseverance is
approaching an
continuing to
altitude
descend on
of
the
5
parachute.
kilometers.
We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Now you can see already dunes on the surface of Mars. They are here.
Valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Mars is orange, it's covered by dust. It contains a lot of
Shell set.
Current velocity
hematite,
is
which is
83 meters per
iron
second
oxide.
at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here in safety Bravo.
And soon you will see
We
a
have
dust cloud when
completed our
the
terrain relative
rover
navigation.
will
Current
approach
speed is about
the
30 meters
surface.
per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the
This
sky
is the
crane,
dust cloud.
about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
And that was a great success, of course. NASA has a big history of big successes with rover landings. And this is not an easy task. Rover has a size of a car almost now, and it contains a lot of scientific equipment, quite often relatively fragile. So, for example, it contains X-ray spectrometers and UV spectrometers to measure surface on the to measure rocks on the surface. There is also radar to measure subsurface, to observe subsurface. There is a weather station to research on atmosphere, and of course there are many cameras. And there is also an interesting instrument to produce oxygen from Martian CO2. And I will come back to this in a few seconds. But before, I want to tell that this rover, of course, collects samples. And for example, these are first two samples collected. You can see these two holes it can drill. And this is a basalt altered with salt minerals, and it may contain some fluid inclusions even, which could have good potential for habitability. And what is interesting, these samples are not only analyzed here, but will be also brought to Earth in late 2020s and analyzed on Earth in addition. So I mentioned about this special instrument to produce O2, oxygen, from CO2. As you know, the Martian atmosphere is made of CO2, so it's a plenty of it, but there is not too much oxygen. And therefore, the idea is to produce this on Mars. So this is, of course, an important propellant together with methane. So if two gases are produced, they can serve as a fuel to launch a rocket from the surface of Mars and to bring it to Earth again. So this is also the view of SpaceX, not only of NASA. So to summarize a little bit, water should be not a big issue, neither propellants. They should be relatively easy to find on the surface of Mars, but metals require more sophisticated methods. And searching for metals is difficult even on Earth. It requires a lot of geological knowledge, a lot of good analytical equipment, geophysical equipment sometimes, and therefore we'll focus mostly on metals in the next part of the talk. So at first, I want to reiterate, this is not about bringing metals back to Earth, but it's about using them on the Martian surface. So we'll not necessarily search for these noble metals, platinum group elements, which are very rich in these asteroids, in some asteroids, and they could be brought to Earth, and we could have an economic growth because of that. It's not this story. It's rather about finding normal metals like iron, cobalt, nickel, also copper, gold, and to use them on the Mars surface. And therefore, NASA is preparing for that. They try to construct or design first robots which could search for ore deposits on Mars. They organize special competitions of these robots. Even ESA started to do the same, and even our European Rover Challenge. Of course, the challenge is not about our prospecting, but it contains some tasks which are similar, such as probing the ground. And I mentioned about different metals that could be used on Mars. Gold is one of the key metals, which is interesting. This is a component of modern electronics. It's highly resistant to corrosion. It has excellent conductivity, and it's also easy to process. And therefore, it will be very useful on Mars. We will need plenty of electronics in the modern society, and society on Mars needs to be modern to be able to communicate with Earth. And gold is associated with many other metals. So one of these group is siderophile elements. So I mentioned about platinum group elements. If we search for gold, we may often find platinum group elements on this occasion. They are all associated with iron-rich minerals and cobalt and nickel-rich minerals. And the other group are chalcophile elements. And chalcophile elements are associated mostly with sulfides. Sulfides look like this. This is a picture from an ore microscopy we use in our geological laboratories. So this is how they look like. They are always yellow, bright. You may know how pyrite looks like. It's yellow, shiny, bright, looks a bit like gold. And here are how oxides look like. So oxides contain siderophile elements, and oxides are also quite shiny, quite bright, but they are gray in appearance. And of course, you can have various sulfides. What we know from Earth, they generally occur together. So if you find one sulfide, for example, sulfide of copper, chalcopyrite, This is usually associated with other sulfides, sulfide of iron, pyrrhotite, or sulfide of nickel, pentlandite. And as I mentioned, we know this from our Earth studies, including oceanographic studies. So this is an example from an IODP expedition I participated several years ago. And we drilled these rocks from a depth of 800 meters. For this, we used this drilling ship. And these mafic rocks on the ocean floor are quite important because they are pretty similar to the rocks which can be found on Mars, which is also covered by mafic rocks. So therefore, we are not surprised that sulfides found on the Martian surface, or rather on the Martian meteorites, as this is an example from a Martian meteorite, Chargotite, which is a basaltic meteorite. So this in basaltic is a mafic rock. So here you can see the same paragenesis, the same association of sulfides. So this is pyrrhotite, iron-rich sulfide. This is pyrrhotite in the earth sulfide. And this is pentlandite, nickel-rich. This is pentlandite. They are quite similar. They only differ by the fact that Martian sulfides do not contain so much copper, so do not contain so much chalcopyrite. And also, rocks are quite similar on the Martian surface. So this is an example from California, and these are so-called basaltic piles. These are hexagonal piles that form during magma cooling. So when magma cools, it fractures and it makes such hexagons. And we can see them also from satellite images on the Mars surface. We have also rover images from the Mars surface. We can observe other rocks. And for example, conglomerates, which are sedimentary rocks, also look quite similar to Earth conglomerates. Finally, something for geographers maybe, we have very similar landforms on the surface of Mars. So this is Arsia Mons, a Martian volcano, one of the largest. These largest volcanoes on Mars are larger than 10 kilometers, like Arsia Mons. Olympus Mons has even more than 20 kilometers. But they are quite similar in appearance to terrestrial volcanoes. Maybe they have larger calderas. But if you look for smaller volcanoes, this is an example of a dike. And dike is underground. The dike is an vertical intrusion of magma in the ground. And this is an array of volcanoes controlled by a dike. So if you look at a similar array on Iceland, you can see similarities between these shapes. Also, hydrothermal vents occur on Mars, and they occur on Earth. This is an example from Yellowstone National Park. We have also volcanic fissures on Mars. This is a beautiful picture taken this year by Cassie's camera. So this blue area is the volcanic fissure. This is covered by basalts. This is a sandy plateau. If you look carefully, you can see even some dunes on the surface. And there are also impact craters visible on the surface, these blue circles. Finally, we have lava channels and lava tubes on Mars. This is how they look like. They are close to Ascreus Mons, another giant volcano on Mars. And this is how they may look like in a zoomed picture. And this is how they look like on Earth. We do have lava channels and lava tubes too. So lava channels are open and lava tubes are closed. There is also a tunnel in the ground that was formed by a flowing lava. And these are quite interesting for scientists because this roof may protect organisms from damaging radiation. So they are very often studied. Finally, the structure of Earth and Mars is similar. We have this triple structure with crust, mantle, and core. And also in the Mars, we have crust, mantle, and core. And what is interesting, we know this for Earth, especially geophysicists know we have liquid core and we have a solid core on Earth. And on Mars, apparently, we also have this situation, at least first results of the InSight mission with a first seismometer on the surface of Mars. They indicate we should have a liquid and probably also a solid core inside. At least we know that at least part of the core is liquid because S waves don't go through it, only P waves. Finally, InSight found also that we have Marsquakes. So these are analogs of our earthquakes. And more than 150 Marsquakes have been discovered already. The largest are probably in Cerberus Fossa, which is tectonically active area apparently. And there were also some literature studies suggesting relatively recent volcanism in this area, maybe as young as 1 million years. And here are some examples. Most of these Marsquakes are very small, but some have a magnitude of more than 4 even. So we know about all this, not only from in situ research on Mars, but also from studies of Earth. And there are so-called planetary field analogs distinguished, which are especially important to study processes on Mars, because they show most similarities with the rocks and with climate of Mars. And for example, Geoplanet Society, which is a society that helps scientists wanting to study planetary processes on Earth. It helps scientists with special fundings for that. And Geoplanet Society distinguished 8 planetary field analogs at the moment. And many scientists, including those from our doctoral school, use these findings, is able to gain these findings. This is an example from colleagues from Space Research Center. They study a hydrothermal system and volcanic system in the Danakil Depression in Ethiopia. We have another study in Spain, in Rio Tinto, aiming at ore formation processes. To better understand ore formation processes, we study them also on Earth using remote sensing from satellites. And this area is very good because it has little vegetation and the climate is acidic, so little humidity. So thanks to all this knowledge that we got from the Earth studies, we are able to distinguish 4 regions on Mars, or maybe better to say 4 types of region on Mars, where we should search for ore deposits. And the first type are magmatic and hydrothermal areas. So this is an example how it works. This is from the oceans. So it can be seawater that is penetrating the ground, but this can be also meteoric water. In any case, water is coming down, it meets magma chamber, and when it meets magma chamber, it gets heated. When it gets heated, it can dissolve more metals, and after that it's ascending. So because it's light, when it ascends and it meets seawater, metals rapidly precipitate because cold water cannot contain so much metals. And therefore, so-called hydrothermal chimneys form, and they form usually in 2 stages. Later, I will talk a lot about sulfates and sulfides. And at the first stage of hydrothermal chimney formation, sulfates form, then after that, sulfides form the internal part. And the difference between sulfates and sulfides is that sulfates are sulfur-based minerals that do not contain much metals, but sulfides contain much metals, and they are interesting for us. And we have this hydrothermal system mostly along mid-ocean ridges, and these are some examples of hydrothermal chimneys. So when the temperature of outcoming water is high, these smokes are usually black. When the temperature is decreasing, it becomes more white. Sometimes at the end, the flow is diffused, and then it just goes with no color along a fracture. And what could be interesting for oceanographers, and I know also people from our institute and from Geophysical Institute are involved. Poland has an area to search for such sulfides under oceans. So this is quite important because this area is allocated for us for 15 years, and there are only 7 countries that have this permission from International Seabed Authority. So it's a good occasion to study sulfides also in the context of Mars. But sulfides and hydrothermal system can occur also on land, of course. So this is an example from Iceland. And when we zoom in, it may look like this. And we will make a movie. I did it if I remember well. And you can see that water is instantly evaporating and it's boiling because the temperature underground is more than 100 degrees. Because the ground with the atmospheric pressure is exactly 100 degrees, and it's precipitated. See how much boiling is just even a micro geyser, and here is a real geyser, how it looks like. Also in Iceland, the same location. And scientists noticed that if we have this hydrothermal activity, sorry, I'm a bit cold. If you have this hydrothermal activity on Mars, it may emit methane into methane atmosphere. So scientists are interested in investigating methane on Mars since 2 decades. This is an example of NASA study from a NASA telescope in Mauna Kea, Hawaii. And this NASA group found some methane, or at least they thought they found methane. It's not quite confirmed yet that we can have so much methane in the Martian atmosphere. But later, other scientists followed up on the studies, and some Italian groups tried to even correlating or modeling these results to show that we have plenty of methane, especially in volcanic areas and hydrothermal areas. So far, we don't have evidence for this. At least it's not validated enough. But certainly there is some methane on Mars. Curiosity rover results indicate that, or at least suggest that. But probably this methane is released seasonally, and maybe it's not so abundant as previously thought. In any case, it seems that in summer, in Martian summer, more methane is released from the ground, and therefore the concentration increases. And then in the winter, the concentration of methane in the atmosphere decreases. These results are confirmed by planetary Fourier spectrometer. This comes from an Italian team, and they measure methane content in the atmosphere on exactly the same day. So they somehow confirmed the curiosity results. And what is important, this was measured in so-called nadir geometry, so perpendicular to the surface of Mars. So this number is based also on the surface measurements. This is the whole profile of the atmosphere. This is important because after that, NOMAD spectrometer and ICS spectrometer, two spectrometers of Trace Gas Orbiter mission, measured methane concentration between 3 and 25 kilometers using so-called occultation mode. So in a mode when atmosphere of Mars was between the sun and the detector, so only high altitudes are possible to measure this way. You cannot measure very low altitudes because of the dust. And they found literally no methane, or at least if there is any, these are PPT levels. So it seems if there is any methane on Mars, it's rather close to the surface. And another important type of areas that could be useful in our prospecting are impact craters. And we know this again from Earth. This is an example from Sudbury, Canada. So this is the mining distribution. These red dots are mines. And you can see that they are distributed around the impact crater. So on Mars, we can expect probably the same, that we could have metal deposits around the craters. This is because we have many craters on Mars due to the vicinity of this planetoid belt, asteroid belt between Mars and Jupiter. But most likely we should focus on craters larger than 10 kilometers here, because these craters are able to induce, the large projectiles are able to induce magmatic and hydrothermal processes. Another possibility to search for our deposits on Mars related to hydrothermal circulation could be areas that were tectonically active, such as one in Valles Marineris, studied also by our colleagues at the Space Research Center. And here, hydrothermal fluids could have migrated along the faults, and it's possible that they brought some metals. This is known from Earth, at least. It's not so well investigated on Mars. But based on Earth studies, we could expect we can find gold or zinc or antimony in these areas, for example, but they are all related to sulfides. And one big problem with sulfides is that we cannot find them on Mars with the current technology. So therefore, at present, we can only search for some associated minerals like mica, quartz, which is also not so easy to find, or siderite or carbonate. Finally, there is another type of area which is very special. It's not high temperature process. It's rather sedimentary process, but everybody knows this very well from the gold rush in Alaska. And in this process, gold grains, this is mainly about gold grains that flow with river, then once the river slows down, the flow slows down, they are preferentially dropped. And this happens because they are heavy, of course. And this happens in different places called placers in English, such as holes, different holes, such as internal parts of meanders when the river slows down, or plant pools under waterfalls, and so on. And you can say, okay, but there are no rivers on Mars, how to search for how to make these deposits. It's true, there are no rivers at the moment, but there were rivers on Mars in the past. So it's easy to imagine that future colonizers walk along rivers and search for gold using quite primitive tools even. That would be possible. But for now, we have only rovers, and rovers also tell us that we do have sulfides. This is a curiosity rover. It's a curiosity rover, so not Perseverance. And the Curiosity rover had already done many discoveries. It's on Mars already a decade. So it took plenty of pictures, it did plenty of analysis. And this is one panoramic picture. If we zoom in, we can see this in an enlargement. And let's enlarge this even more. And here we can see a trace after Curiosity drilling. Curiosity was also able to drill, but it was also able to analyze rocks on the surface using XRF instrument. And so this is an example. And here, this is dust. Dust is orange, but of course, Curiosity cleaned this rock from the dust, and the rock is kind of gray or basaltic composition. And here you can see a trace after an analysis. Here we can see results of such an analysis. And Curiosity is able to estimate metal contents. So, for example, in this place was quite rich in zinc and copper compared to other Martian rocks represented by this wrapper line. And Curiosity found also sulfides. This is also from Gale crater. And this is the abundance. So this rock contained about 2% sulfides. These were mostly pyrrhotite with minor pyrite. And this was detected with X-ray diffraction analysis, ChemIn instrument. So X-ray diffraction is a mineralogical analysis and not chemical analysis. But we can see sulfides also in the Martian meteorites, as I said. So this is an example we did from computer tomography. This is a CT image. And here we can see that ore minerals, which are these bright points, are called opaque because they are not transparent in microscopic, in geological, petrological microscope. These are ore minerals, oxides and sulfides, and there are quite many in the ergotites. Here is an example I showed before already, and we currently study many Martian meteorites at the Institute of Geological Sciences. We try also to combine this with remote sensing analysis, especially from the ExoMars mission. So I already talked about this NOMAD and ACS instruments that mission has. These are for trace gas analysis, but there is also the color camera I mentioned about also, and I haven't mentioned Space Research Center, one of the Geoplanet institutes has worked together with other institutions from abroad to build this camera. So this is what we use, but we use also instruments from NASA missions, especially Mars Reconnaissance orbiter. It has infrared spectrometer, near infrared spectrometer called CRISM, Compact Reconnaissance Imaging Spectrometer for Mars. And it serves to map the surface of Mars in terms of mineralogy. And it works like this, that you have different spectra emitted by different minerals. And if you see this green spectra, you have such mineral. This is low calcium pyroxene, so orthopyroxene. And here is another mineral. So, for example, olivine is purple, and so on. But we are interested with hydrothermal minerals because these are related to metallogenesis, to ore formation processes. And there were also sub-studies. This is from an Arizona group, and they mapped hydrated silica deposits near a volcano. This is a Nili Patera volcano. And this is the map they did. And they know this is hydrated silica because, so these are from Mars, blue, green, red, blue, green, red, and this is also the spectrum from Mars, and they compare this to a spectrum from Earth, and therefore they know this is hydrated silica. And of course, we try to find hydrated silica also in our research. This is a study of our student, Katarzyna Ignatowicz. She found hydrated silica near from Askreus Mons, a volcano I mentioned about before. And there are also other minerals that we try to find hematite, for example. This is a study from Gale crater made by another student, Kasper Rudik. So this is a spectrum of hematite, of course, with addition of other minerals. So these spectra are not always as ideal as reference spectra, but they presumably contain a lot of hematite. We were also very interested with sulfides. As I mentioned, sulfides are associated with sulfides. Sulfates are associated with sulfides, so ore forming minerals, and therefore we are very interested with sulfates. And this is kieserite, magnesium sulfate. This is done by another student, north from Valles Marineris. This is an example from Olympus Mons, jarosite detection. This study has been done at the Space Research Center by another student. And here it's an interesting example because we found two different sulfates in one area, Cerberus fossé. I talked about Cerberus fossé before because this area is tectonically active recently and also volcanically active, and therefore finding traces of hydrothermal activity, there are mineralogical traces, is quite significant. But we can find only sulfate. So we found jarosite, which is iron sulfate, and alunite, which is alumina sulfate, but we are not able to find sulfides. This is because sulfides have weak spectral features in the near-infrared range, so they interfere a lot with silicates. I talked about orthopyroxene before. It is quite common on the Martian surface. Also, cyanopyroxene has a similar spectrum. So if sulfides occur always actually with orthopyroxenes and cyanopyroxenes, it's impossible to distinguish them. And therefore, maybe it's worth to search for sulfides in other ranges, in far infrared range, for example. So between 20 and 30 microns, and many pyrites, many sulfides, including pyrites, yellow, chalcopyrite, orange, they show excellent spectral features in this range. So these are some laboratory analyses, but oceanographers also see these spectral features in remote operated vehicles research when they study hydrothermal vents in infrared. So here is also pyrite and chalcopyrite, and also astronomers see these spectral features around 25 microns in planetary nebulae. So we thought maybe it's worth to study them on Mars. So far, there is no high-resolution instrument capable to study sulfides on Mars. and to work in far infrared on Mars. And therefore, we are working on a design, on this cooperation of two institutes. And this is possible because in far infrared range, there are not so many atmospheric interferences neither. On Earth, far infrared is not very well applicable because we have heavy interferences with water. On Mars, we do not have so much water, so any interferences are relatively small. CO2, which could be the issue, it's very abundant in the Martian atmosphere, is have lines mostly in smaller wavelengths. So also, what is important, silicates are not so problematic. So this is the same scale. Sulfides show very strong features. Silicates show quite weak spectral features on these sulfide lines, and sulfates also. And therefore, we did a modeling, and it seems like having 20% pyrite, we should already see it from the orbit. So I said we'd like to operate in a relatively good resolution to cover an area of about 60 meters. 20% makes about 12 meters of 60 meters. So this is not very common on Earth, but there are many examples where we have massive pyrites covering this kind of this field, this size of field. So therefore, we hope in this small contribution, we will be able to participate at least to some extent in this global new race for Mars and its resources. And I hope many of the doctoral students of the Geoplanet School will also be able to participate with us. And thank you again for your attention, and I welcome questions.
Thank you very much for an interesting talk. So we have time for questions. Please, if you want to ask a question, raise your hand on Zoom. Any questions for our speaker? Okay, Michał Różyczka, please.
You showed a map with Martian-like sites or environments. I would just like to add another one site like that, namely dry valleys near McMurdo Station in Antarctica. This is very Martian-like environment.
So you mean this map with planetary field analogs, right? I guess.
Yes.
Mm-hmm. Okay. Thanks for the tip. So Antarctica, right?
Right. Dry valleys.
Dry valleys. I will write this down. It will be interesting to write about this.
Okay. Thank you
very much.
Okay. Question from Wiesław Macek.
Yes, you have mentioned that there's a difference between the earthquake and the similar phenomenon on Mars, that there's no S wave. Usually on Earth we have S and P waves for beginning of the earthquake. Why do you think there's a difference on Mars?
All right. Maybe I was not clear enough or too fast. What I meant, we have no S waves coming through this zone.
Yeah.
So
that I meant, yes. no S wave.
Yes. So therefore, it's inferred it's probably liquid. And we have the same situation on Earth, that we have liquid core, at least internal part of the core, and therefore we have no S waves, right, through coming through this liquid core.
Okay. Question from Masayuki Wada.
Hello, thank you for a nice talk. It's not the scientific question, but I'm curious. So it seems like from the first part of your talk, it seems like there are many the governments or companies are interested in, how can I say, developing the society in on Mars or Moon, right? Am I correct, right?
Yes.
Are there any treaty or some organization regulate this the development?
Yes. So there is, for example, this organization. They make every year so-called global exploration roadmap, but it's not very strict organization. It's quite loose. So there are also some conventions regulating, and maybe some lawyers hear us too. Maybe they can more. I know there are in the community, but as far as I know, there are some conventions also regulating how can we extract ores from Moon or Mars, but they are not very specific, and also not all countries want to obey this rule. So Chinese, for example, seem to be quite independent. They do not show a lot of information either. It's quite a wild field at the moment, and it's difficult to predict what will happen.
Okay, so basically first come, first serve basis. Maybe it's important to invest now. Okay, I see.
Right.
Thank you so much. Did you, maybe I missed, but did you mention about the water source on Moon?
So actually, this talk was about Mars, so I didn't speak about Moon. That was probably the only time I showed Moon in this talk. But if you are interested with something, maybe I can try to respond.
Yeah, I just want to know the are there any source of water on the Moon, like ice or?
Right. As far as I know, there should be some in shaded areas, and there are also water-bearing minerals. Maybe not so many as on Earth, but there are. That could be another source. And generally, we should be able to get some water. Also, even ilmenite captures some gases into its structure, and including water, but these are trace amounts. So maybe this is not the most important source. But generally, yes, scientists expect to find water, and there are many specialists also in the Space Research Center who study this. I remember Gordon Wasilewski, for example. I think he will have a talk the day after tomorrow at the Space Mining Conference. Will be in Krakow on Wednesday and Thursday. I think it will be streamed online, so I recommend the interested people to follow this conference because it has a similar topic and it's quite interesting. I will also be there.
Thank you.
Thank you. Other questions? Yes?
May I, Romana Radkiewicz?
Yes, please. Please.
The Space Research Center. What is your opinion about the goal of the humans on the Martian surface about, I understand, 2040? Do you think that it is really possible to get there?
I think not in the public sector. I see this as an optimistic, like first possible day in an optimistic variant. So it will be rather later, in my opinion, at least.
Okay, thank you very much, and thank you very much for very interesting talk.
Thank you very much.
Any other questions? Well, I have one. I was quite surprised to see that in a single museum in Vienna, they have like 5 big pieces of Martian rock. So how many Martian meteorites we have on Earth?
Right, we have about 500, between 200 and 300 different types of meteorites. And they are classified into several major groups. And on this picture, you see meteorites from 3 major groups, mostly ergotites. There are many of them, about 200 almost. Then there are maybe about 30 nuclides, and then there are several asignites. So these are 3 major types. But altogether, we have almost 300 different meteorites. And there will be more and more. People are still searching, especially on deserts and also on Antarctica, where there is not so much vegetation.
And can we already link those specific group to some geological formations or on Mars? Or?
Oh yes, to some extent, yes. So, for example, one can say that shergotites represent most of shergotites represent superficial magmatic rocks like basalts, but there are also because shergotites are classified into 3 subgroups. But let's say general, they are generally basalts, and asignites, for example, represents ultramafic rocks of mantle composition, more like mantle composition. So to some extent, it's possible, yes.
Thank you. I see no other questions. Let me look at the chat. Nothing here. So once again, thank you very much for a very interesting talk. And I wish all of us a very successful and interesting academic year. Thank you very much.
Thank you again. Also, it was an honor for me to talk today. I'm very happy. Thank you very much.
Thank you.
Thank you.